From Cape Canaveral Air Force Station in Florida, ULA presents live Atlas V launch coverage. At Space Launch Complex 41, an Atlas V rocket is fueled and ready to launch GPS-2F-12, the 12th and final next-generation global positioning system satellite for the United States Air Force.
Ready to go for launch. Roger, go for launch.
T-minus 3, 2, 1.
Atlas engine ignition.
Liftoff of the United Launch Alliance Delta IV Heavy rocket.
Hello and welcome to Mission Control at the Atlas Spaceflight Operations Center. I'm Andrea Casillas. Thanks for joining us today for ULA's first launch of 2016. We are on track for liftoff at 8:38 a.m. Eastern Standard Time at the opening of today's launch. We have a 19-minute opportunity with the launch window closing at 8:57 a.m. The launch count is currently holding at T-minus 4 minutes, and the team is not working any issues. This planned 30-minute hold is the final hold and the 6-hour and 20-minute launch countdown, and allows the launch team time to conduct final systems checks and resolve any outstanding issues prior to entering the terminal count at T-minus 4 minutes. GPS-2F-12 delivery on orbit is scheduled to take place 3 hours and 23 minutes after liftoff. Because of that long duration, we'll conclude live coverage at about 20 minutes after liftoff. However, before we sign off, two guests will join me here in Mission Control. Lieutenant Jason Fischbach from the Global Positioning Systems Directorate and I will discuss the Air Force's role in providing worldwide 24/7 GPS capability. And I'll discuss Boeing's role in designing and building the 2F series with Dan Hart, Boeing's Vice President of Government Satellite Systems. An Atlas V rocket is launching the 12th and final satellite in the Air Force's GPS-2F constellation. This is the Air Force's 60th operational GPS satellite, all delivered to orbit on ULA's Atlas and Delta rockets. The Global Positioning System, or GPS, is a space-based positioning system consisting of a minimum of a 24-satellite constellation, providing navigation and timing information to military and civilian users all around the world. The signals are so accurate that time can be measured to within a millionth of a second, velocity within a fraction of a mile per hour, and location to within a meter. GPS is a critical enabler for the United States military to provide national security and a worldwide service for billions of civilian users. Built by Boeing, the next generation 2F series provides improved capabilities for military and civil users, and a new third civil signal, L5, for commercial aviation and safety of life applications. The launch team recently received a final briefing from 45th Space Wing Weather Officer Clay Flynn. The weather for this morning's liftoff is within the launch commit criteria. The probability of violating launch constraints is 40%. The ground winds are 22 knots, gusting to 26 knots out of the north-northwest, and the temperature is 51 degrees Fahrenheit. So the weather looks favorable as we proceed towards a planned T0 of 8:38 a.m. Eastern Time. ULA is using the Atlas V 401 configuration to launch GPS-2F-12. This is the 61st Atlas V evolved expendable launch vehicle flight since the inaugural launch in 2002, the 31st flight of the 401, and ULA's 104th mission. A number of important milestones took place leading up to launch. The Atlas V launch vehicle is produced in Decatur, Alabama, and Harlingen, Texas. It is comprised of a Common Core booster powered by the NPO Energomash RD-180 main engine and a Centaur upper stage powered by the Aerojet Rocketdyne RL-10C. The GPS-2F-12 satellite is protected during ascent by a 4-meter diameter payload fairing. Launch processing here at Cape Canaveral began with the arrival of the Centaur second stage on December 18th, followed by Atlas V booster arrival on December 20th. The Atlas V booster was erected on its mobile launch platform inside the vertical integration facility on January 11th, with Centaur stacking a day later. A week later, on January 19th, the GPS-2F satellite was encapsulated inside the 4-meter payload fairing. Then on January 30th, the encapsulated payload fairing was transported to the vertical integration facility and mated to the Atlas V booster. Yesterday, at approximately 8 a.m., the fully integrated Atlas V on its mobile launch platform was rolled to the pad at Space Launch Complex 41. Track mobiles are used to transport the mobile launch platform to the launch pad, which is a quarter-mile trip that takes about 30 minutes to complete. Once the mobile launch platform reaches its park position at the pad, the team conducts final securing. Following pad clear, at about 4 hours before liftoff, the Atlas V is fueled and configured for launch. The Atlas V rocket stands 189 feet tall, or about 19 stories, and weighs more than 700,000 pounds fully fueled. To lift the Atlas V away from the pad, approximately 860,000 pounds of thrust is produced by the RD-180 engine. This is Atlas Mission Control at T-minus 4 minutes and holding. The GPS-2F satellites are part of the 4 generations of operational GPS satellites on orbit. With a total of 30 operational satellites, GPS is the largest constellation in the Department of Defense, as well as the most robust and capable system in the history of space. From their vantage point in the semi-synchronous circular orbit, the GPS-2F satellites provide improved accuracy through better clocks and a longer design life. Here's a video detailing GPS-2F-12's trip to orbit.
The following profile details the important events of this mission using approximate times.
5, 4, 3, 2, 1, 0. And liftoff of the Atlas V rocket.
The Atlas RD-180 main engine ignites to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 78 seconds. At 90 seconds, the vehicle experiences maximum dynamic pressure. Approaching booster engine cutoff, the Atlas V is burning propellant at the rate of 1,600 pounds per second, traveling at approximately 16,000 miles per hour, and located 62 miles in altitude at 146 miles downrange. Booster engine cutoff occurs approximately 4 minutes after liftoff. 6 seconds after booster engine cutoff, the booster stage is jettisoned. The first Centaur main engine start takes place 10 seconds after booster separation. The payload fairing is jettisoned approximately 4.5 minutes into the flight. Cutoff of the Centaur main engine follows an approximately 13-minute burn. The mission now enters a 3-hour coast phase. At 3 hours 17 minutes into the flight, the Centaur main engine is started for a second and final burn. This burn will last approximately a minute and a half. Following the second Centaur main engine cutoff, the mission enters a final 5-minute coast phase. At 3 hours 23 minutes, Centaur releases the GPS satellite for the United States Air Force.
This is Atlas Mission Control at T-minus 4 minutes and holding. This morning's flight is dedicated in memory of retired ULA employee Kirk Webbink. During his 34-year career at Martin Marietta, Lockheed Martin, and ULA, he designed harness installations for the Titan II, Titan IV, and Atlas launch vehicles. One of Kirk's proudest accomplishments at work was his part in the design of the Manned Maneuvering Unit, or MMU, used by the astronauts on the Space Shuttle program. Kirk was both a supportive coworker, sharing his wealth of design knowledge, and a consummate professional, always able to deliver a quality product while adapting to design changes and keeping with the rapid launch rate. Kirk was also a caring individual, dedicated to his career, family, and friends. He was well respected and always willing to lend a helping hand. Kirk was an avid stargazer, and his star shines bright above us today. With this morning's mission, we also remember Aerojet Rocketdyne employee Thomas Davis. Tom joined Pratt & Whitney in 1961. As a young systems engineer, his first assignment was on a relatively new rocket engine program called the RL-10. Over the next 54 years, Tom would dedicate 46 years of his career to the RL-10 program. Known to his co-workers and customers as Mr. RL-10, Tom knew everything about the engine and was responsible for training generations of engineers on the performance and operation of the RL-10. During his career, Tom played a key role in several major events that built the strong legacy of the RL-10. This included the first in-space firing of the world's first liquid hydrogen, liquid oxygen fueled rocket engine, the development of 13 derivatives of the original RL-10 engine that have powered Atlas, Delta, Titan, and Saturn upper stages, the direct involvement in over 14,000 firings of the engine, which accumulated more than 2.3 million seconds of engine hot fire time, and the successful launch of numerous military, government, and commercial satellites to orbit, and powering space probe missions to explore every planet in our solar system. Tom will forever be fondly remembered as Mr. RL-10 and deeply missed by his colleagues and friends. This is Atlas Mission Control at T-minus 4 minutes and holding. In a few moments, launch conductor Ed Kidda will pull the team for the final go to pick up the countdown. 27 engineers and managers will be pulled for system status and readiness to proceed. This is a final status check before launch for all vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The readiness pull includes hydraulics, pad water deluge system, electrical system, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as launch conductor Ed Kidda performs the final pulling of the team.
Status check to proceed with terminal count. Atlas systems propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Water. Go. Centaur systems propulsion. Go. Pneumatics. Go. LO2. Go. LH2. Go. Half gas. Go. Electrical systems airborne.
Go.
Ground. Go. Facility. Go. RFFDS. Go. Flight control.
Go.
Com.
Go.
Timer.
Go.
GC cube.
Go.
Umbilicals. Go. ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator. Clear to proceed. Launch director.
LD is go. The launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count. T0 is planned for 1338 Zulu. Set count to start at 1334 Zulu.
T0 is set for 13.
Polling is complete and the team is given the go for launch. The countdown will resume in approximately 2 minutes. From T-minus 4 minutes until launch, you will be listening to launch conductor Ed Kidda and his team performing the final steps in the countdown procedure. You'll hear the team confirm securing of the Atlas liquid oxygen topping, followed by the call to transfer the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur liquid hydrogen and liquid oxygen topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed with the verification of the Centaur tank pressures. A final status check of Atlas, Centaur, and GPS IIF-12 readiness is conducted at T-minus 25 seconds. Seconds before liftoff, the RD-180 engine ignites and performs a health check before lifting the vehicle off the pad. After liftoff, you'll hear the voice of Marty Milanowski providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
2, 1, mark.
3:55.
The countdown clock is resumed and we are proceeding towards an 8:38 a.m. Eastern liftoff.
Three minutes. Securing LO2 topping.
Atlas tanks to flight pressure.
250.
FGS internal.
T-minus 2 minutes, 30 seconds and counting. Once the rocket lifts off, it will only take about 78 seconds to reach Mach 1, or the speed of sound.
$159.
Vehicle internal.
$155.
Launch sequencer start.
$150.
Securing Centaur LH2.
Securing Centaur LO2.
$140.
FCS launch enable.
FGS armed.
T-minus 1 minute, 30 seconds and counting. The launch vehicle payload, vehicle, and ground systems and Eastern Range are a go for launch.
120.
OCUs armed. FCS count started.
110.
Vent valves locked.
60 seconds.
T-minus 1 minute.
$40.
Stable at step 3.
T-minus 30 seconds.
25.
Status check.
Go Atlas.
Go Centaur. Go GPS.
20. 15. 10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. RD-180 ignition. And we have liftoff of the United Launch Alliance Atlas V rocket carrying the 12th GPS-2F satellite for the United States Air Force. The Global Positioning System provides worldwide positioning, navigation, and timing service for military and civilian users.
Control.
You are hearing the voice of Marty Milanowski, here providing launch vehicle ascent data.
Speeds and injector pressures continue to look good. RD-180 continues to perform well. And the roll program is now complete. Body rates look good. Engine performance continues to look good as well. Coming up on Mach 1 momentarily. Mach 1. Body rates continue to look very good. Engine performance is steady. Max Q, booster has throttled back as expected. Engine signatures look good. Body rates continue to control right down the middle. Current altitude is 13 miles, downrange distance 8.5 miles. Current velocity is 2,200 miles per hour. Booster performance continues to look very good. Body rates are smooth. Coming up on our closed loop steering segment. And closed loop steering has been enabled. Also a minor roll. RD-180 pump speeds and injector pressures continue to look good. RCS pyro valve has been fired. System's now pressurizing to flight levels. Signatures look good. Booster performance continues to look very good at this point. Pitch yaw and roll, controlling right down the middle. We've ended the Q alpha limited steering and throttled back as expected. Engine signatures look good. Coming up on our 5G throttle segment. And we have begun throttling to maintain 5Gs. Boost phase chill down is underway. Signatures look good. Pump temperatures are as expected. And we've begun throttling to 4.6 Gs in preparation for BECO. Boost phase cool down is complete. And we have BECO. Engine shutdown looks good. And we have stage separation. Looks like a clean SEP. We have LOX and fuel pre-start on the RL-10. GN2 purge firing's underway. We have RL-10 ignition and full thrust. Coming up on payload fairing jettison, and we do have indication of a good payload fairing jettison. All signatures look good at this point.
This is Atlas Mission Control at T plus 4 minutes 40 seconds. We've just heard Marty Milanowski report the successful execution of the events comprising the early part of today's mission, and all systems to continue to operate nominally. The mission is currently in the first of 2 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 12 minutes. I'm now joined by the Air Force's Lieutenant Jason Fischbach from the Global Positioning Systems Directorate. Lieutenant, thanks for joining me today.
Thank you for having me. It's an honor.
Great. Can you tell me just a little bit about yourself?
Okay, as you said, I'm Jason Fischbach. I'm from the Republic of Panama. I come from a family of enlisted veterans. I'm married. I have 2 wonderful sons. When I was growing up and we didn't have enough money for college, it became an easy decision to join the Air Force. So I joined the Air Force about 18 years ago, and after balancing school and work for about 15 years, I finally earned my bachelor's degree in electrical engineering. Shortly after that, I became the first person in my family to become a commissioned officer, and I've been working with the GPS Directorate ever since. I started off 3 years ago with the GPS Directorate. The first 2 years I worked as government lead for the GPS-12 production line, and that was an awesome opportunity. I saw everything from every stage of build and test of the GPS-12 satellites. Then I went on to what I'm currently working, which is the next generation command and control system.
Great. Well, congratulations on all you've accomplished so far. That's quite a feat.
Thank you so much. I really appreciate it.
Since you're very knowledgeable about the GPS program, can you kind of give us a current status on the GPS constellation?
Of course. The GPS constellation remains stable, healthy, and robust. With 30 operational satellites on orbit, the constellation is comprised of 19 GPS-2R and 2RM satellites and 11 GPS-2F satellites. The GPS-2R and 2RM satellites, also known as the GPS legacy satellites, have exceeded their life expectancy. In fact, 18 of the 19 that are on orbit today have exceeded the 7.5-year design life. Regardless of that feat, they continue to provide reliable position, navigation, and timing services.
That's great. You know, I'm really glad because of the lifetime of the satellites is kind of ending here. I'm glad we're helping you launch a new one today.
Yes, the GPS-2F satellites are vital to the modernization of the constellation, and in order for us to maintain the level of reliability and precision that GPS delivers to users worldwide each and every day.
Can you tell me about some of the capabilities that the 2F satellites bring to the GPS constellation technically?
Of course. The 12 Boeing-built GPS-12 satellites have improved signals, which will enhance the precision of the global position navigation and timing services provided both to support both the warfighter and the growing civilian needs of our global economy. The GPS-2RM was the satellite that directly preceded the GPS-12 satellites, and it introduced the L1 signal, one new L1 signal, and it introduced 2 new L2 signals. The GPS-2F satellites introduced 1 new L5 signal. So L1, L2, L5, what all that means is it's just basically a portion of the frequency spectrum. The L1 signal carries probably the most commonly known signal, the L1 course acquisition code, and that's the most commonly known because that's what you're going to have on your GPS watch, your GPS navigation system in your car and stuff like that. The L1 also carries a code called precision code, PY code, and that's for military applications, and it also carries L1M code. The L2 frequency carries L2C, which is a modernized civil signal. We'll talk about why that's important here in a sec. The L2PY, precision code for military applications, and L2M for military applications as well.
Great.
The L5 signal, which is brought by this GPS-2F, is safety of life. It's going to be used for safety of life applications, including aviation applications. The great thing about the GPS-2F satellite is that it has all those signals on board in the navigation payload. And those signals carry information like the GPS date and time, satellite ephemeris, satellite state of health, and ephemeris is basically the location of that satellite. And it also includes almanac information, which is all that other information for the rest of the satellites in the constellation.
Great. Powerful satellites.
Yes. One last thing I wanted to mention was that modernized signal, what that has, that enables this thing called ionospheric correction, which will greatly improve accuracy to all the users.
Amazing. So we've talked a lot about what we've done in the past with GPS. Can you tell us a little bit of what's in store in the future for the GPS program?
Yes, the GPS program has a lot of modernization efforts currently underway across the space, ground, and user segments. Those modernization efforts include improved or stronger signals. It includes additional civil signals. It includes improved robustness of the overall system architecture, and it includes advanced user or advanced receiver techniques for the GPS military user equipment.
Great. So in terms of your satellites, what's next for GPS?
Okay, so we just, as you see, we just launched the last GPS-2F. We're going to be the next satellite that's currently in development is known as the GPS-3 satellite. Its first satellite, SV-1, has just completed baseline thermal vacuum testing, or TVAC. As you know, TVAC is one of the most comprehensive, perceptive, and critical tests that we have in use today. It's where we take the satellite, we subject it to space-like environment, so a simulated space environment.
Test like you fly.
Exactly. And then we review how the subsystem performs. So this gives us insight on how the satellite will actually perform once it's in orbit.
That's great. So can you tell me a little bit about what capabilities that GPS-3 will bring to the GPS constellation?
Yes, GPS-3 is going to bring stronger signals, which will improve our resistance against jamming and spoofing. And jamming is basically, think of you have a radio station that you like, 88.1 megahertz, let's say, and there's a transmitter over here that's broadcasting more powerful signal on that same frequency. Well, you're not going to get what you're expecting. You're going to get whatever that other transmitter that's boosting at a higher power. So this greater power improves our resistance to jamming and spoofing. Another thing that this GPS-3 satellite brings is it brings additional civil signal, the L1C. It's a fourth civil signal. The cool thing about this civil signal is that it's internationally interoperable. And what that means, it will be able to communicate with Europe's navigation satellite, Galileo. I think there's plans in the future for other satellite constellations to do, the navigation constellations to do the same thing. The last thing I would say is that GPS-3 boasts a 15-year design life, and that design life would noticeably increase the longevity of the GPS constellation. So the first satellite, SV-1, is projected to be available for launch in August of 2016. That available for launch date, it doesn't say that's when we're gonna launch the satellite. It just says this is when the satellite's completed its build and test phase. The actual launch date will be based off a couple of factors. One of them being the availability of a launch vehicle to take us to orbit. The other is operational priorities, and the last thing I would say is the availability of a ground system, a control system that we'll be able to harness the capabilities these new satellites bring to bear.
Great. Sounds like quite a powerful new satellite.
Yes.
So thank you so much for joining me today. I know that I really enjoyed learning more about the satellite and what we're launching today, and I know I'd be lost without GPS, so thanks for joining me.
Me too. Thanks for having me. Thank you.
No problem.
Appreciate it.
In just a few moments, I'll speak with Boeing's Dan Hart, but before that, let's take a look at a video.
The Global Positioning System is a marvel of the modern age. It consists of more than 30 GPS satellites circling the globe over 12,000 miles above us. In tightly controlled orbits, these U.S. Air Force satellites continuously transmit their signals to Earth. An extraordinary technology, GPS enables anyone with a GPS receiver to determine their precise location and the exact time anywhere in the world, usually within a meter and within a billionth of a second.
GPS is ubiquitous. It's everywhere. It's in our cars. It's in devices that you use to determine how far you've run or ridden your bicycle.
With billions of users and countless devices, it is easy to take GPS for granted. But it is the essential platform for innovations which enables us to do everyday things like buying gas at the pump and getting directions. And amazing things like tracking ice melts and saving lives in ways that were formerly impossible.
The beauty of the GPS system is that it's available for everyone. The cost of entry for any user is simply the cost of their receiver.
Boeing helped make GPS possible. It's been the U.S. Air Force's prime contractor on 4 major programs, replacing the initial group of satellites as their service lives were completed. Overall, Boeing has produced 2/3 of all GPS satellites, more than 40 in all.
Satellites are normally built in a low volume, perhaps 2 or 3 at most. And they're usually sit in one spot, and resources are brought to the satellite.
Now, to ensure that GPS is available whenever it's needed, Boeing has changed how satellites are made. It's producing 12 new GPS satellites using a streamlined process based on its efficient and advanced airplane assembly line techniques.
Our goal is to have the highest quality.
These new satellites bring next-generation performance to the GPS constellation we all use every day. As a result, they are delivering new levels of accuracy to what is already a remarkably accurate system, and they are being built in a much more efficient way. day, ensuring that this essential technology is available when we need it.
This is Atlas Mission Control at T plus 15 minutes and 30 seconds into the GPS 2F-12 mission, and all systems continue to operate as expected. The Atlas Centaur second stage and GPS satellite are currently located over the North Atlantic Ocean, southeast of Greenland. Our next event, the first Centaur main engine cutoff, or MECO-1, is scheduled to take place in about 2 minutes. Here's Marty Milanowski.
Fuse controlling down the middle. Body rates are steady. 1 minute to MECO. All Centaur systems continue to look very good at this point in the burn. Approximately 20 seconds to MECO. And we have MECO. Engine shutdown looks good. We have RCS 4S settling. Fuel tank is being vented.
This is Atlas Mission Control at T plus 17 minutes 30 seconds. Marty Milanowski just confirmed MECO-1, or cutoff of the Centaur RL-10C engine. The mission has now entered an extended coast phase, which will last approximately 3 hours. Following MECO-1, the mission trajectory changes from a southeasterly heading, flying over Eastern Europe, Turkey, and Saudi Arabia. It will continue in a south-southeasterly direction over the Indian Ocean. Following a short second burn of the RL-10C engine, Centaur will deliver the GPS 2F-12 satellite to semi-synchronous orbit over the southern Indian Ocean, south of Australia. Separation will take place about 3 hours and 23 minutes after liftoff. Because of the long duration of today's flight, we'll be concluding our live coverage here shortly. But now I'm lucky enough to have Boeing's Dan Hart, who's the Vice President of Government Satellite Systems from Boeing. Dan, thanks for coming here today.
It's great to be here.
You know, why don't you start off by telling us a little bit about Boeing's support to the Air Force and the GPS program over the last 40 years?
Well, you know, at Boeing, this year we celebrated our 100th anniversary as a leader in aerospace.
Congratulations, that's quite an amazing feat.
Thank you, and I see no better way to start our second century than with the launch of GPS 2F-12. GPS is such an incredible example of how aerospace technology has improved and changed our lives over the years. And 40 of those 100 years have been spent in working on the GPS constellation, the technology, and the long domain excellence that has allowed us to get to where we are. We have supplied 540 satellite years of GPS operation up to this point, and look forward to many, many more. And this is our 50th GPS satellite delivered into orbit. And that's a huge source of pride for everybody, all 160,000 employees across the Boeing company.
Quite an illustrious career you have here. Talking about all of the Boeing satellites, I'm very impressed. Again, congratulations. I'm excited that we get to be a part of your launching today.
It's a great business.
So because you are so knowledgeable about the satellite systems, can you tell me about some of the key components of the satellite and what that means to the timing and navigation mission?
Well, GPS-2F has a number of improvements over previous satellites, and it's the most capable GPS satellite in orbit today. Some of the improvements are an improved clock, and the clock is the heart of the satellite, so improved navigation for everyone. There is a jam-resistant military signal on the GPS-2F, supplying an assured capability for all of our military in harm's way. There's also a new civilian signal on the GPS-2F, the L5 signal, which provides capabilities for commercial aviation and also search and rescue. And the GPS-2F has programmability, additional capability that allows us to adapt and maintain performance throughout the satellite's life.
That's great. Quite a lot of functionality that's housed in that one satellite.
Every 2F that goes up improves the performance of the entire constellation.
That's amazing. So in terms of the satellite life, can you tell me a little bit about that from all the way from its design through to its life expectancy?
Well, the design life of the 2F is 12 years. However, most of our satellites last much longer than that. As a matter of fact, we have one satellite, SV-23, which was launched 25 years ago and is still in operation.
Wow.
It's older than many of the people who are working on it. And that's a real testament to the women and men who designed, tested, built, and operate it. We take our satellites through a very, very rigorous program, from the selecting of the parts to the testing of the components and up through the spacecraft. We put everything through, everything from rigorous vibration environments to make sure they can survive launch, to really extreme temperature swings in our thermal vacuum chambers to make sure the vehicle will last reliably throughout its entire life.
After you telling me all of the things that you do to qualify your satellites, I'm not surprised that their lifetime has been much longer than expected.
They've performed really, really terrifically.
That's amazing. So it's hard to compete with your last 100 years of being a company, but tell me, what's next for Boeing and GPS?
Oh, we're very excited about the future. Across our government and commercial satellite programs, we've been heavily focused in driving cutting-edge leaps in digital payload technology and incorporating those into all of our programs. And that's how we see GPS evolving. Much the same way as smartphones have changed the way we communicate and brought us incredible capabilities. From the old days of analog phones, we see similar breakthroughs coming through for GPS and other programs. And so we see a GPS constellation in the future that's much more resilient, much more affordable, and much more capable, and really able to very capably serve the Air Force and serve as the gold standard for position, navigation, and timing for generations to come.
That's great. Well, Dan, thank you so much for joining me today. Again, congratulations on an amazing day, and hopefully good luck for today's launch, and thanks for joining me.
It's been a great day. We look forward to the rest of it.
Great.
Thanks.
We'll complete our live coverage with another look at today's liftoff, which occurred at 8:38 a.m. Eastern Standard Time. Please visit ulalaunch.com or join the conversation on Twitter and Facebook for more information about the Atlas V. I'm Andrea Casillas. On behalf of the entire launch team, thank you for joining us and have a great day.
Go Centaur. Go GPS.
20. 15. 10.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. RD-180 ignition. And we have liftoff of the United Launch Alliance Atlas V rocket carrying the 12th GPS-2F satellite for the United States Air Force. The Global Positioning System provides worldwide positioning, navigation, and timing service for military and civilian users.